When an object is thrown horizontally, the object has width. Okay? There are two things involved there. We need to understand the motion, the component of the motion horizontally and vertically. So if you remember in our lecture notes, we obtained something wonderful there. We obtained the governor equation to help us understand this expression, this phenomenon. So, and we try to break it down into two. And in our tutorial question 11, we solved the first part, which is the movement of that object horizontally. What about vertical? Thank you for watching. That is what we want to solve in this video. So you can go back to our tutorial question 11 to check what is there. But in this video here, we want to solve this problem here, which is a second order ordinary differential equation. And as you can see here, it's quite different from the first one, because we know that gravity is a big problem. You know, in an issue of anything in physics, we also talk about this gravity. And recently there's been a kind of information on black hole. It's another problem too. And experts, they were pointing our attention to the issue of gravity. So if you go back to our lecture note, you know how we come up with this gravity in the governor equation. But in this video, we want to solve this problem. Of course, it has two conditions as well. Second order ordinary differential equation, it has two conditions. If you want to solve third order, you will need three conditions. If you want to solve fifth order ordinary differential equation, how many conditions do we need for that? That's fine. Very simple. So let's start. We can rewrite this expression to give us this, because we know that y dot dot is second derivative of y with respect to t. Y dot is the first derivative of y with respect to t. So we have our equation 7 of our lecture notes. So let us try to use something. You know, this one here, it's a non-homogeneous, because we have minus g, so it is non-homogeneous. But one thing is that we can actually reduce this equation 7. How is that possible? Let's introduce p to be dy dt. If our p is dy dt, then we can see that equation 7 and 8, they are the same thing. I didn't do any big deal there. Look at it very well. Look at it. I didn't do any big problem there. So I only reduced the problem to first order. So upon this, we can actually proceed and solve our equation 8, which is the first order. But another thing we should notice here is that this problem here is a linear. And whenever you see a problem like this that is linear, then we are going to use the method of integrating factor. When you get to second 200 level, you know, you'll be taught more about this. But in this video, I will try to solve the problem so that all of us can capture what is there. But why do I even call it a linear? You can see here that this linearity here, it can easily be expressed as one thing. Let me show you what it's all about. Let's first of all capture our integrating factor. How do you get the integrating factor? We consider the coefficient of p here, the coefficient of p, which is k. Okay, so let's use that one to get our integrating factor. So integrating factor now be exponential, the integral of the coefficient of p dt. What is the coefficient of p? Is k. Then we have dt. So if you integrate k, you have t. Then this will give us exponential kt. Then next thing is for us to multiply both sides of equation 8 by the integrating factor. Don't forget, this is our equation 8. You see the equation 8 now. So we have dp dt plus kp equals minus g. So we only need to find our integrating factor, which is exponential kt. So we multiply both sides of equation 8 by this integrating factor to give us this, as you can see now. But back to my question earlier, that why do we call this kind of problem linear? You see now that it's a linear because everything on this side, everything this side here, it can be represented as the p dt into bracket p, which is the unknown variable we are looking for, multiplied by the integrating factor. Let me show you what I'm trying to say now. If you keep exponential kt, you keep it here and you differentiate p, you have exponential kt dp dt. Likewise, if you keep p and you differentiate exponential kt, you have k exponential kt. So you now say the linearity now. The linearity means that this first order linear ordinary differential equation, after we can simplify it by using the integrating factor, we can integrate both sides. Yes, look at it very well. This part here is the same thing as d dt of p exponential kt. What do I mean? You keep exponential kt, you differentiate p, you get the p dt. You keep p, you differentiate exponential kt, then you have k exponential kt. Okay, so let's now try to integrate both sides. Now what I've done is this dt here, this are dt, it can come to this side, dt can come to this side. Okay, so we have this like this, then we integrate both sides. Upon that, we can find integral will take care of the derivative d, then we have p exponential kt like this. Then this one, what about this one too? This is integration this time around, so you differentiate exponential kt, then you have it to be k, then you divide it by it, then plus the constant of integration, which is c1. So we cannot divide both sides by the integrating factor, which is exponential kt. So it will come down here, it will come down here. So we now have minus gk exponential kt. This exponential kt will cancel the one at the numerator. Then if you bring it down again, you have c1 over exponential kt. The exponential kt will come up, then it will become exponential minus kt. Then what we need is yt, not p. Do you agree with me? You know, we started the problem by saying that our p equals to the y dt. So if our p is the y dt, we need to return that p back to equation 9 to give us the y dt is equals to minus g over k plus c1 exponential minus kt. So this is the problem now. So what do we do now is that we can also make our dt to go to the other side. Then after that, you can integrate both sides to give us this. So by the time you integrate this one, we see clearly that we're almost through with the problem. So if you integrate the y, you have y. Then if you integrate minus g over k, you have t. Because this here, it means that t raised to power 0. And how do you integrate t raised to power 0? That would be t raised to power 0 plus 1 over 0 plus 1. So then you integrate this one again, which is c1 exponential minus kt, then divided by minus k. Then plus the constant of integration again, which is plus c2. But let's simplify this. Let's make it better. So we can actually write our d. Let's introduce another constant d to be c1 over minus k, which is this problem here, this one over this. Then we can also say our c equals to c2. Then we have our y of t is equals to c plus d exponential minus kt minus gt over k. We need to find our constant c and d. We need to find constant c and d. So let us use y of 0 equals to 0 and y dot of 0 equals to 0. Let's subject equation 10 to the first condition, which is y of 0 is 0. So look at it. Y of 0 equals to what? C plus d exponential minus k of 0 minus g of 0 over k. So here we only change our t to be 0. Yes, we change our t to be 0, and when we have this expression. So this implies that our c plus d is equals to 0. What do I mean? Look at the exponential minus k times 0. Any t raised to power 0 is what is 1. 1 times d will give us the, then we have c plus d is equals to 0. If c plus d is equals to 0, what does it mean? It means that c is equals to minus d. So let's use the second derivative, second condition. For us to use the second condition, we need to know that it's a derivative. Because if an object is thrown horizontally with a particular speed, which is speed v0, in the upward direction, the speed is 0. That is how we come up with this, like I've explained in the lecture notes. So with this now, we can differentiate this equation 10 that we're familiar with before. If you differentiate it, if you differentiate c, constant c, you have 0. If you differentiate exponential minus k, you have minus k. Then this will give us d multiplied by minus k, then exponential minus kt. Then if you differentiate gt over k, you have gk. You have gk. So let's proceed. Then this, we cannot impose our y of dot of 0 equals to 0. Then if we impose this one, we have this expression here. Then we can proceed and discover that indeed minus kd is equals to g over k. I only make it the subject of formula, okay? Then which means that our d is minus g over k squared. So we've been able to obtain our c to be minus d, and we obtain our d to be minus g over k squared. Then what is c? So if you do it very well, you put d in the first expression, which is minus d. Then you can see that our d is g minus g over k squared, while our c is minus g over k squared. So finally, we can go back to our equation 10, which is this one that, remember that we imposed the first condition on this. We also use the second condition to get our d and c. So if we substitute it, you now see that this is what we're going to obtain. Then very simple, we can just factorize g over k squared, then we obtain this. So we can now see clearly now that this is how we obtain the expression which we're going to use later. Thank you for watching. Bye.